Chris is going to talk about installer plugins and how they can be potentially abused. I'm also really interested to see how, in his talk, he's going to describe how you can leverage, for example, the endpoint security framework to perhaps detect malicious activity. So, round of applause for Chris.
Thank you for coming to my talk, Plug and Play using native code to get initial access with installer plugins. What kind of motivated me to do this talk was a couple of years ago, Patrick Wardle tweeted out some odd behavior he saw with an unsigned bundle being loaded into the installer app. And it turned out this was actually an installer plugin, and it's legitimate functionality in macOS for installers. And so I looked into it and devved up a quick POC to load up a malicious installer plugin in the installer app, and I learned that it's possible to do what's known as swizzling to basically hide the installer once the user closes it. And so you could have the installer app run your malicious code in the background, and the user would have no idea that it's still running after they hit close. And so sometime between then and now, Apple changed the behavior of the installer app and installer plugins such that it starts a XPC service for your plugin. And so that created a bit of a dilemma for me because once the installer app was closed, that XPC service would die. And so in this talk, I'll talk about how we can overcome that challenge with two different techniques and how we can possibly detect this kind of behavior. So who am I? I'm a lead offensive security engineer for Zoom. I've been there for almost a year. And when I started out my career, I primarily focused on Windows, PostX, and tool development, but all it took was one red team against some macOS endpoints, and I pretty much fell in love at that point. There wasn't a lot of research at the time and not a lot of offensive tradecraft that focused on macOS, and so I decided to just jump on over and focus on that. And so that's kind of what I've been doing since then. And so also I work on Poseidon, which is a Mythic agent developed by Cody Thomas. So I do that in my spare time, but I also like to build offensive tools in Objective-C, Golang, Python, Rust, you name it. So today I'll talk about some well-known techniques that have already been talked about today with installer packages. I love them because there's so many different places where you can execute code, but this part I'll kind of skip over very quickly because it's already been reviewed. So then I'll also jump into how installer plugins work and talk about the internals. And then we'll talk about two different techniques we can use to basically get over that problem of the XPC service dying once the installer app closes. And then we'll talk about some possible detections with the endpoint security framework. So what are installer packages? Essentially, they are bundle files that are in a ZAR archive format. They can have any number of files that will be installed on the system. They can contain installer scripts. So like we said, the pre-install, post-install, or pre-flight. They can have those. Also can contain plugins, which I'll talk about today. So now we'll talk about some of the execution techniques that have already been covered today. So first are installer scripts, and as I said, there are many different places where you can execute code as an attacker during the install process. And so you can use a installer script that uses any pre-installed scripting service on the system. So it can be Python, Perl, PHP, Ruby, Bash, anything. And I also learned recently that you can actually use a Mako binary in place of these instead and just have it kick off native code within that binary. And also the package script service is actually responsible for kicking off any installer scripts that you include, so that's just something to note. So this is just an example post-install script. So you have the normal bash shebang, and this is a pretty common way for me to get initial access on ops, is using OSA script with a command line or one-liner to go out and reach out and download some JavaScript payload. Also, there's installer JavaScript. This is essentially inline JavaScript that's contained within a distribution XML file. And so you have special product archive packages that have sometimes smaller packages contained within, and with those you can edit the distribution XML and include some inline JavaScript. And as mentioned before, you can use the system.run or system.run-runts methods to execute arbitrary commands on the system, and so you can use that to get initial access. So this is just an example distribution XML file, and you'll see within that CData block, that's just a simple installation check, and that runs before all the files are copied to the system. And so as an attacker, we can do any kind of checks to check to make sure we're not running in a VM or get some system information, and then run and kick off our payload. All right, so now I can dig into the installer plugin internals, now that we kind of covered the basics of installer packages and the different code execution techniques. So installer plugins, these are essentially also bundle files that are included with installer packages, and you actually need to use a product archive to include these. So you would have to build either like a simple flat package that doesn't have a script, or a simple component package that installs some file on disk for you and then includes a post-install or pre-install script. And so you would take that and then package that up in what's known as a product archive. And there are a bunch of command line tools that'll do this for you, or you can find any third-party apps that'll build these for you. And so essentially the installer plugin has a plist file that defines when your installer plugin is going to get loaded in the installer app. So you can have it load at the beginning or at the end of the install process. It doesn't really matter because that only deals with the UI. The installer plugin is actually loaded once the installer app starts, and it detects that you're using a custom plugin. And so what's neat about this for attackers is that we have access to Objective-C. So we can call any of the native macOS APIs, we can start a new process, we can make network connections using some of the networking libraries. The options are kind of limitless. But the one problem, as I mentioned before, is that once the installer app is closed by the user, that XPC service is killed. And that's because that service is packaged with the installer app, and the installer app actually invokes that service. So with installer plugins, once the installer app starts up, it actually loads a series of bundles, and there's a bundle that corresponds for each installer pane. So for the introduction, the license, the README, those are actually bundles that are contained within the installer app. And so it goes and loads each of these bundles. There's one specific bundle that is interesting, and that's involved with installer plugins, and that is the remote plugin bundle. So once that bundle is loaded, it actually uses the NSXPC connection API to make or reach out to the installer remote plugin service and start that service. And once it makes that connection, that plugin service will load your attacker bundle from some random location on disk. And what's kind of interesting is that it always is a randomized temporary location, so it's kind of difficult to build detections based on just that path. And I know that installer plugins are legitimately used sometimes, so that may not be something you want to base your detection logic for. So internally, whenever that remote plugin service is started, there is a function within the installer section remote plugin review controller class. This class is responsible for basically navigating through each of the installer panes, and each time it loads a bundle, there are a bunch of different methods that it calls, like will enter pane. This is basically code that's executed before you click next or get into the next installer pane. And then there's another method called did enter pane, and that's code that's executed once you click on next and enter the actual pane. And so within that remote plugin service, that class method, there's a path for your bundle that's passed into that method, and it's used in what's called an NS block. And so a block is just a function or code that's executed in the background, and you basically pass a function that is executed within that block. And so that function gets past the bundle path and an instance of the installer remote plugin service view controller. So what happens inside that function is it uses the NS bundle class to initialize an instance of that object with the path. And so once you have an instance of an NS bundle, it just calls load. And so if you're an attacker, you use something known as a constructor to execute code within your bundle at that point. And so it calls NS bundle load, and it loads your attacker bundle. And then if you want to do something like spawn a new process or inject some code into another process, you would do something like that in there. In this case, the installer plugin is running in a user context, so you don't have access to things like getting a handle to another process or a task port, but you can do some other interesting things. And so also, after it loads that bundle, it will basically take the class methods and proxy those from the installer app to your bundle. And so the did enter pane, will enter pane, those methods will be proxied to your custom bundle and execute code that you have in there. So now that I've talked about the installer plugin internals, I'll talk about two different techniques that you can use to execute code and kind of get out of that temporary XPC service. So the first is using something called XPC. And so XPC is essentially remote procedure calls on macOS. And so in Jonathan Levin's course, he talked about a lot of the services on macOS use XPC in the background. And so one of the command line utilities, LaunchCDL, actually uses XPC to talk to LaunchDaemon or LaunchD. And so as an attacker, we can use the same functionality to send XPC messages to LaunchD and submit a job. And so a job is basically a temporary LaunchDaemon or launch agent on macOS. And so we can use a special function called XPC pipe routine to send a message to LaunchD and start that job. And what's really cool about this is that basically any process in userland can do this. You don't have to be signed or entitled. You can just send messages to LaunchD and start a new job. So when you do that, the installer plugin will send an XPC message to LaunchD, and then XPC proxy will kick off your temporary service for you. So this is what the XPC code looks like. This is actually taken from Jonathan Levin's tool, LaunchJTL. This is a open source version of LaunchCDL that he developed. And so the source code, all it does is create an XPC dictionary and fill it with the parameters you need to submit a job. And so you'll set keep alive to 1, because if something happens to our payload and it crashes, we would like LaunchD to restart it. Also, we submit the label. This is just the name of the temporary service. Program arguments you can use or you can omit. It doesn't matter, but the program in this case I'm going to use to provide a path to my payload. So then once we have all the parameters set, we create that small XPC message, and we use that XPC pipe routine method to send a message to LaunchD. And so this is just what it looks like over the wire. Again, Jonathan Levin has a neat little tool called XPOCE that you can use to inspect XPC messages in LaunchD. So you'll basically use the tool and point it at LaunchD or PID1, and it'll inject a library to hook a special function to print out each XPC message that it receives as a string. And so it's a neat way you can trace XPC messages between processes. And so this is just what it looks like over the wire. So now for the second technique, we are going to abuse Electron apps. And we've already kind of talked about the environment variables that you can use with Electron apps to essentially run them as a normal Node.js application. But for Electron apps, they need special entitlements with the hardened runtime. So if a developer decides they want to ship their Electron app to users over the internet, they have to have it notarized. And so for that, they have to use the allow.jit and the allow executable memory entitlements, just for Electron to work how it normally does. So what's also cool is a lot of the Electron apps, for some reason, use the disable library validation and allow DILD environment variables entitlements as well. I found this to be quite common. There's actually a site, I think it's called electron.js. I'll drop a link later in Discord. But there's a ton of Electron apps listed there, and most of them have all 4 of these entitlements. And so you can find a legitimately signed and notarized app that uses these entitlements. And this is what we need as attackers to inject into the app. So with those 2 environment variables that we need for injection, one, we have DILD insert libraries. So this is something we can use as a classic technique to inject a dilib. And then we need the Electron run as node environment variable. And so with the Electron run as node, basically you want to tell the app to hide itself or hide the window. And the reason being is if the user sees after they run your installer package some window just popping up on the desktop for an Electron app, that's very suspicious. And so after they run the installer, we want to hide that activity from the dock and from the UI. So you can pass an argument that references the Electron class or module and just tell it to hide from the dock. Also, there's a special flag you can tell Electron to basically break on the first line of JavaScript in any Electron application. And so I did that because I ran into some issues where once the app was running, for whatever reason, I couldn't get a reference to the Electron module. It just wouldn't be found. But I found that if I stopped the application before it actually executed any JavaScript, for some reason, it actually worked. So that's the reason why I included that flag. So here's what the code looks like. So for this example, I chose the Twitch app. Through my testing, this was probably the most stable app. I tried a bunch of other apps where once I tried to hide the window or eject the library, for whatever reason, the Electron app would just crash. So Twitch was the most stable. And so Twitch is actually really, really large. It takes maybe 3 or 4 seconds to copy to disk through the install process. And so I found out that if I tried to call a special function to launch the Twitch app, before it was copied to disk, it would just fail because it actually wasn't installed at the time. And so I used the dispatch async function to execute code in the background after sleeping for 8 seconds, just to make sure that the Twitch app is copied to disk. And then I would use a function discovered by Reggie to basically launch my application using launch services. And so I just added arguments for breaking the Electron app, or setting the, or breaking and starting the debugger, and then also passing in the Electron code to hide the window. And so we also include the DILD environment variables, variable, or I'm sorry, the DILD libraries environment variable. And we also include the Electron run as node environment variable. So we pass those on to the ls open URL with roles function, and that executes our Twitch app. So now I'll just run 2 quick demos showing both methods. So the first one will be the one for submit job. And basically I have a Mythic server running in the background. And I built payloads, one Poseidon and one for Apfel, to make or establish a C2 connection when the payload executed. So the first thing we'll do, we'll open up the package in Suspicious Package. I'm sure most people are familiar with it, but if not, it's an awesome app to inspect the contents of package installers. You can look at all the included files, any scripts that are included as well. And so if we go to the All Files tab, we'll see that we're just copying a simple Mako binary to the library folder. And this binary is just a Poseidon payload. So once it's executed, you'll see a new Poseidon callback. But yeah, you can also look at the scripts tabs and see any scripts that are going to be executed as well. So now we'll close the suspicious package out, and then we'll just double click on the submit job package. So once you hit allow, this is actually when your installer plugin is loaded into that remote process. So just because you see that the second pane is for my custom plugin, this is not when the code is executed. So my code for submitting the job to LaunchD has already ran at this point. So now once the payload is copied to disk, you'll see it kicked off by LaunchD and give us a new callback. So we're going to go ahead and type in our password. Once we hit enter, it'll copy the payload file to that library folder, and then we'll immediately get a new callback. All right, so let's submit job. Now we're going to do Electron. So pretty much the same thing with Electron. We can open it up in Suspicious Package and look at the contents. We can see that it's going to copy the Twitch app, and you can note the size is 387 megs, so that's pretty large. So that's why I have to work on the timing and executing the code in the background and sleeping. And then it also copies a dilib to the library folder. So you could include the dilib with your app, but in this case, this is something that's already signed and notarized, so we don't want to ruin that signature. Then we'll close that out, and then we'll double click on the Electron app or package. And we're going to kind of speed through this because we want to make sure that our Twitch application is copied to disk before my code executes. So then once it copies the Twitch app, it'll go ahead and call that launch services API and inject our library in there and run Twitch in the background. And so you can see at the bottom of the dock, Twitch is actually not running, so you don't see any windows pop up, and there's no dock icon for Twitch. And so we can open up Task Explorer and look at the Twitch app, and then search the dilibs and see that our appfel payload is loaded into that process. All right. So now we'll talk about ESF and detection considerations. So we all know the endpoint security framework allows vendors to tap into macOS system events and subscribe to process events, file I/O, module loads, and library loads. And Apple has effectively kicked all the vendors out of the kernel. And so it kind of reduced some of the visibility. But what's cool about it is that developers can now get access to the same telemetry. And so that's why you saw a prevalence of a bunch of tools. Patrick Wardle came out with File Monitor and Process Monitor. Super Hacker Steve came out with Crescendo. I worked on AppMon, which is based off of a lot of code in FileMon and Process Monitor. But yeah, it was really neat. So I do like the endpoint security framework. There are some shortcomings, but it's still a really useful framework for detection. So first, we'll talk about the submit job attack indicators. This is an event that is common between both, so I won't talk about it when it comes to Electron, but you're going to see an mmap event or a memory mapping event for our custom bundle inside of that installer remote plugin service. So that's just something to note. It's probably going to be very difficult to build detection logic based on just this file path because it's always random, so it'll never be the same. So yeah. And this is the basically process execution events from Crescendo. First, we see that XPC proxy kicks off or calls my temporary service with the bundle ID or label name for that service. And then you see subsequently the payload gets kicked off. One thing to note is that in ESF, it's kind of hard to tie in the true parent PID for processes. I believe that's something that is coming down the line where you actually can pull the true parent. But for right now, it's still listed as PID1, which is launchd. So that makes it hard to really track down those relationships. Also, you can use tools like LaunchCodal to pull additional information about a process. What kind of led me to there was looking at Jaron Bradley's research with TrueTree. He did a lot of his research basically looking at the proc info command and all the information that it outputs. One weird thing is that the responsible PID in this case was listed as itself. So that kind of confused me and threw me for a loop. I didn't understand why that was. But luckily, the path attribute pointed to the true parent, which was the installer remote plugin service and the proper PID. But that makes it kind of difficult for analysts because this is not offered by the endpoint security framework. You have to do some extra legwork to get this. So this is the TrueTree output. It's just showing that the true parent of our payload is the installer remote plugin service. Now with the Electron app, kind of the same thing happens. XPC proxy kicks off the Twitch app with that special bundle ID, and then you see the process execution event. Now, one thing I guess you can build detections for this specific technique with Electron apps is those command line arguments. So seeing the debugger flag or the flag to start the debugger, and then also the arguments to hide the app. Electron apps are probably normally not started that way, so that's definitely odd behavior and something you may be able to build detection logic for. But I could easily use some other app that allows us to inject a library. I know Firefox is one. Reggie already talked about this, but Firefox actually uses the DILD environment variable normally with that process to inject like I guess like an interposed library with some plugin host they have. And so you might see some normal behavior with that, but it's just something to note for detection logic. And so this is the proc info information once again. We see that this time the path attribute points to running board D, which is something kind of new to me. I assumed that it was going to be launchd or the installer remote plugin service, but I guess Running Board D also starts new applications as well. Also, you can note in the environment variables that the DILD insert libraries variable is there. So that's a pretty neat way to pull out that information. And maybe you can build some detection logic based on just that. Once again, the responsible PID points to itself, so super confusing. I don't know why that is, and hopefully that's something that Apple can rectify in the future. And then once again, the true tree output, it points to Running Board D with the PID. So that's the true parent of our Twitch application, which kind of makes sense since Running Board D normally starts applications when you double click on or use the open command of that nature. All right, and that's pretty much it. So thank you, Patrick, for the process monitor and file monitor code, Jerron Badley's research with TrueTree, Reggie with the API call, Jonathan Levin for all his research and his training. You can visit the GitHub links for example code. Those are just 2 Xcode projects as well. But thank you.
Have you seen attackers abuse these techniques, or even show interest in that, or you think that's something we'll see in the near future, or what are your thoughts on that?
We were actually talking about this at lunch. I don't think there's any attackers using installer plugins at this time. Like, I haven't seen anything, mostly because I guess the old techniques still work, so why use new stuff?
Any other questions?
For the UI injection, why don't you have issues with like signed UI lists or injecting them like the Apple does some many mechanisms for that?
Yeah, so the 2 entitlements I talked about in that slide, the allow DILD or allow unsigned libraries, I can't remember the exact name, but that entitlement allows you to load unsigned libraries into that process. And so that combined with the DILD entitlement allows me to inject unsigned libraries into that target app.
You can find an app that has that.
Yeah, basically. Yeah, and there's Electron, it's pretty common just because of the way the Electron framework works. You'll at least find the allow executable memory and the other entitlement, but for most times you might find all 4 of those entitlements. So yeah, it's pretty common with Electron apps. All right, thank you.
Man, we love Electron apps, huh? Thanks, man. That's awesome.